Alright, this is the video for my Math 1325, my Business Math 2 or Business Calculus class. This is the video for sections 10.2 and 10.3 and 10.4, so it's quite a bit. This video is working on the assumption that we have already done 10.1, which is what we should have finished on Wednesday the, I want to say 21st, which is tomorrow. If for some reason we don't quite finish that, then sorry, but we're going to assume that we've already done that section. In order for this class to move forward, I am begging every student in my business calculus class to watch this video and watch it again and watch it again and watch it again. Play with the homework. I will have my phone with me. I will have my computer with me over Thanksgiving. You can text me. You can email me. I cannot promise you an instant reply. I will be busy, but when I can, I will get back to you. So please, 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 please do this. Okay. Again, I'm working on the assumption that we've already done 10.1. So I'm going to kind of summarize some of the things from 10.1 that we have done. I'm going to go ahead and date this for the 19th, yes, which is the Monday after Thanksgiving. That's the day we're not having classes. The 10.1 stuff that we did so far in the review, we talked about the first derivative and how it can be used to calculate maximum and minimum points. And honestly, we had already done some of that back in chapter 9, at the end of chapter 9. So just to review from 10.1, critical points are solutions of the first derivative equals 0 and values that make the first derivative undefined, which for our purposes usually means makes the denominator of the derivative equal to 0. At critical points, you can have a maximum or minimum. So maxima and minima, remember that's plural. And collectively, these are called extrema, plural for extremum. Extrema means a high or low point, are located at critical values. Critical points, excuse me. Now be careful. This is not saying that all critical points are extrema. It's simply saying that all extrema are critical points. It is possible, and maybe I should write this down, but not all critical points are extrema. Now I'm doing this prior to having actually taught you 10.1, so let's see how good I am at predicting what I'm going to do when I teach that section. I bet that we saw this example in 10.1. If you have f of x equals x cubed, so we all know what that graph looks like by now. Looks like a parabola with left ends pointing out. If you take its derivative and get 3x squared and set that equal to 0, divide by 3 and take the square root, you get x equals 0. To get the y value, you always go back to the original function. So 0 comma 0 is a critical point, but notice that it's not an extremum, excuse me. So the point I'm making is just because you saw the derivative equal to 0 does not guarantee a high or a low point. A critical point doesn't mean it's necessarily an extrema, but if you're an extrema, then you're a critical point. I should be specific. If you're an extrema for a continuous function, then you're a critical point, but not vice versa. Alright, so how do we determine whether it's a maximum or minimum? Remember to determine max versus min, and it may not be either. It may be a flat point, if you will, or what's going to be called an inflection point. This is where we made what the textbook refers to as a sign chart, sign diagram. I mean a sign diagram. Specifically, if you make a number line and put your critical values on it, so I keep saying critical values. Critical values of the x's that you find, I keep using lingo from, no, it's in this textbook. Critical values of the x's that you find, the critical point is the ordered pair. So I need to back up here and correct some of the terminology. Critical values are solutions to the derivative equals 0, or values that make the derivative undefined. Critical points are the ordered pair. So, real fine distinction. Critical values are x values. Critical points are x's and y's put together. But to determine a max or a minimum, use the sign diagram. So let's pretend for a second that you found some critical values. We'll call them C1, C2, and C3, just for the sake of referring to them. And let's just say, for the sake of discussion, that this first critical value made the derivative equal to 0. The second critical value made the derivative undefined. And let's say that the third critical value also made the derivative equal to 0. A sign diagram is where you pick a number on either side of the critical values, plug them into the derivative, and see if they come out positive or negative. So for example, let's say over here, the first derivative came out positive. And let's say here it came out negative, and positive. So these are the, I guess I should write this. First derivative comes out positive, negative, negative, positive. And you can find that out by just plugging in numbers on either side of the critical values. Remember that a positive first derivative means that your graph is increasing, and a negative means it's decreasing. So to be a maximum, you have to switch from increasing to decreasing. So for example, at C1, this would be the location of a maximum, because your graph goes up and then goes down. At C3, this would be a minimum because your graph goes down and goes up. But at C2, this is not a critical point. Its x value is a critical value, but its point is not a critical point because it's either a maximum or minimum. What does happen there? A variety of things can happen there. The fact that it's undefined means that it's probably a vertical tangent line. Could I draw a graph that does this? Yeah, I could. Am I going to right now? No. Why? Because it's 5:45. And I have a lot to talk about between now and the end of this. Okay, so that's kind of what we did last time. We talked about what the first derivative told you in terms of increasing, decreasing, in terms of maximum and minimum. 10.2 is primarily about the second derivative tells you. The second derivative tells you something called concavity and how to locate something called an inflection point. Here's what you need to know from 10.2. And again, here's the title of it. Concavity and inflection points. Before we find them, I want to make sure you know what these things look like. Concavity is a description of whether a graph is bowed upwards or bowed downwards. For example, if I draw a parabola like this is called concave up. And if I draw an upside down parabola, this is called concave down. It's not the same as increasing and decreasing, because notice that the left one is decreasing then increasing, and reverse over here. It's an issue of whether or not you're bowed upwards or downwards. One way to think about it is what would happen if it rained on here. If you're concave up and it rains on you, you gather water. Rain, 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 rain. But if you're concave down and it rains on you, the water runs off of you. You don't gather water. So think of concavity as whether or not it would hold water if it rained on it. And a graph when concavity changes, that's called an inflection point. So let's pretend that you have a graph that looks like this. Now it's fairly clear on the left it's concave up, and on the right it's concave down. That's where the water would collect over here. Now, if you're concave up and suddenly you're concave down, then somewhere in the middle you have to switch concavity. Looks like it's about right there. The place where it switches concavity is called an inflection point. So before we go looking for these things, I want to make sure you know what they look like. Concave up collects water, concave down, the water runs off of it, and where it switches between the two is called an inflection point. Now, how do you find it? Here's how you find it. If there's an inflection point, at x equals c, then either second derivative at that c is 0, or the second derivative at c is undefined. So it's kind of like the same thing that we did for extrema, except with the second derivative. So first derivative tells you increasing, decreasing, max, min. First derivative tells you increasing, decreasing, and extrema. Second derivative tells you concave up, concave down, and inflection points. One other thing about concavity, if your second derivative is 0, it might be an inflection point. But when it comes to second derivative being positive or negative, concave up is when your second derivative is greater than 0, and concave down is when your second derivative is less than 0. And that kind of makes sense if you know that it has something to do with the second derivative. Concave up, second derivative is positive. Concave down, second derivative is negative. So we're going to milk the first derivative for as much information as we can. Where's the extrema? Where's it increasing? Where's the graph decreasing? And we're going to milk the second derivative for as much as we can. Where's the graph concave up? Where's the graph concave down? And where's the inflection point? Now be careful. Just like with the extrema, this is not a reverse simplification. In other words, if your second derivative is 0, that is not a guarantee that you're an inflection point. For example, let me write down what I just said. But the second derivative equals 0 doesn't guarantee an inflection point. Sorry for the sloppy writing. You should be used to it by now. For example, let's take f of x equals, let's see, that would be good. F x equals x squared, 2x, let's go x to the fourth. Okay, that'll work. If you take the second derivative, when we want to fast forward to it, you would end up getting 12x squared. And if you put that equals 0 and solve it, you would get x equals 0. However, if you graph x to the fourth, it will look like a parabola with a flatter bottom. Insert joke here. This is not an inflection point. It is a minima, extrema if we want to be more generic, but it's not an inflection point. So even though 0 makes the second derivative of this equal to 0, there's not an inflection point there. So be careful, because just because the second derivative is 0 doesn't guarantee you're an inflection point. What does guarantee you're an inflection point? If your concavity changes. So how do you determine if the concavity changes? You see if the sign changes. You make a sign diagram with the second derivative. So how does it all look out? How does it look like when you play it out from beginning to end? Well, let me find an example out of the book and just milk it for all I can. Let's see. Oh, come on, give me a good example. All right, this is example 4 on page 657. You're given y equals 3x to the fourth minus 4x cubed minus 2. I'm going to write that down. Y equals 3x to the fourth minus 4x cubed minus 2. Example. This was example 4 on page 657. And the instructions are find the extrema and inflection points. Excuse me. Find the extrema and inflection points. I'm going to start abbreviating inflection points, IP, and insert a joke there. As a shorter right. Alright, when it comes to the extrema, it's all about the first derivative. So let's start by finding the first derivative. First derivative of this is 12x to the third minus 12x squared. Oh look, the 2 disappears. And now I need to solve this equals 0. You're going to have to do some factoring on these. This one's pretty easy. You can factor out a 12x squared. Let me stop for a second. Your best strategy for this video is to watch it. If you're going to take notes real fast, you're going to get behind. Watch it, and then if you want to take notes, go back and watch it again, or pause it. How nice to have a pause button for a teacher that doesn't know when to stop talking. But I am going to move this forward a little bit faster than a normal class, since you have the ability to rewatch it and pause it as you see fit. Alright, so if you solve this, if you factor it, you get 12x squared times x minus 1. Set each factor equals 0. And then solve. You'll get 0 and you'll get 1. Now be careful, these are critical values, but these are potential extrema. There's no guarantee that any of them are extrema. They are critical values, they may not be critical points. How do you find which one they are? Well, make a diagram. Let's put 0 and 1 here, because those are my critical points. And I want to figure out, is the first derivative going to be positive or negative on either side of these? Now, I already know it's equal to 0, so I'm going to write 0 above those to say the first derivative is 0. If I want to figure out what happens on the left of it, I need to plug in a number to the left of 0, like -1, into the original first derivative, into the first derivative, which was 12x cubed minus 12x squared. When you fast forward through the math, if you do all the math here, you're going to end up getting -24. So I know my first derivative is negative over here. In the middle, I would need to pick something like 0.5, and as annoying as that is, oh well, suck it up and deal with it. Get out your calculator and mash the buttons. Oh gosh, I gotta do all this now. Let me see if I can cheat. 0.5 squared is a fourth. By the way, I'm plugging it into the factored version. 0.5 squared is a fourth of 12 is 3. 0.5 minus that is negative 0.5. You ought to get negative 1.5. Again, I'm just trying to expedite things. But what it tells me is it comes out negative. So negative, 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 negative. And then I've got one more interval to check. I need to try something greater than 1. And pardon me, I need to back that up. I don't know if you caught it. I'm plugging these in the derivative, and I forgot to say that I'm plugging them into the derivative. It's very easy to go to the wrong function, but I am plugging into the derivative. Let's plug in 2. Let's do it a little bit faster. If you plug 2 in here, you're going to get 48. Plug it in if you don't believe me. But it comes out positive. And really, that's all you're concerned with. Honestly, I can figure out if it comes out positive without plugging it in. I know that plugging 2 into 12x squared will come out positive, and plugging 2 into this factor will come out positive. Positive times positive is positive. It also explains why everything over here is negative. Plug anything into 12x squared except 0, and it will come out positive. Plug in something less than 1 into x minus 1, and it comes out negative. Positive times negative is negative. Alright, so what can I figure out from the sign diagram? I can figure out that this graph is decreasing. Did I mention this on the first page? Give me 1 second. I didn't actually write it here. I said it, but I didn't write it. But when you're a positive first derivative, you're increasing. When you're a negative first derivative, you're decreasing. Alright, ooh, that looks nasty. I need to write bigger and slower. I know that this graph is decreasing on negative infinity to negative 0, which is the leftmost interval, and 0 to 1, which kind of tells me it flattens out in the middle. And I know it's increasing on 1 to infinity, which is the right end over here where the derivative is positive. Now, who's a max and who's a min? Well, that's when you switch between decreasing and increasing. And they only switches at 1. It switches from decreasing to increasing, which means there's a max at 1, comma, whatever you get when you plug 1 back into the original function. If you plug 1 up here, you get 3 minus 4 minus 2, which I think is negative 3. Again, I'm going through this quickly because you can stop and do the work yourself to verify that f of 1 equals negative 3 without me having to pause right now. There's no extrema at x equals 0 because there's no change in increasing and decreasing. What the graph probably does is it goes down, flattens out, and goes down again. There's probably going to be an inflection point there. But there's what we got from the first derivative, where it's increasing, where it's decreasing, and where the extrema are. Now, as far as the inflection points and concavity, that all comes from the second derivative. So, time for a new page. Second derivative. Second derivative of this one, if I remember the first derivative, is 36x squared minus 24x. Let me go back and check that out real quick. Where's the first derivative? There it is. 36x squared, 24x. Yeah, that's right. Alright, so we need to put that equal to 0 and solve. 36x squared minus 24x. Again, a little bit of factoring here. You can factor out a 12x. That would leave 3x minus 2. These factors get put equal to 0 and solved. So I'm going to get x equals 0 again, and I'm going to get x equals 2/3. Now be careful, these are potential inflection points. This is trying to say IP. They're potential inflection points. In order to verify whether or not they're inflection points, I need to set up a sign diagram for the second derivative. So, second derivative sign diagram. My potential inflection points are 0 and 2/3. Those are a little too close for my liking, but they are what they are. I do know that the second derivative is 0 in both of those. Now I need to pick numbers from each interval to see what happens to the second derivative. For example, let's say I plug in -1. For the sake of time, let's just say that you plug -1 into the second derivative. If you plug -1 in here, it looks like you're going to get 60. Wow. Hey, that's okay. It came out positive. Now be careful. We're talking derivatives. Excuse me, we're talking second derivative. And the second derivative tells you concavity. I know this graph is concave up over here because the second derivative is positive. Now, as far as a number between 0 and 2/3, there's no need to get fancy. You can think decimals. Something between 0 and 0.6666, like 0.5. If you plug 0.5 into the second derivative, let me see if I can figure this out. Half of 12 is 6. Half of 3 is 1.5. 1.5 minus 2 is -0.5. I think you get -3. I'm pretty sure you get -3. I know you get negative something. Let's hope it's 3. And again, in terms of concavity, this means concave down. Now here's what I know so far. At 0, there's an inflection point. My concavity just changed from concave up to concave down. Now as far as on the other side of 2/3, I only need to pick something greater than 2/3, like 1. If I plug 1 into the second derivative, I'm going to get 12. That's positive. That means concave up. I'm going to start abbreviating a bit more. CU means concave up, so you can guess what I'm going to write for concave down. Alright, so here's what the second derivative tells me. It tells me that my graph is concave up on -infinity to 0 and 2/3 to infinity. So not a lot of room in between where it's concave down. And it's concave down on 0 to 2/3 x intervals. And I do have inflection points. I had 2 inflection points. One of them is at 0 because the concavity changes, and the other one is at 2/3 because the concavity changes also. Now, what are those inflection points? Well, I got to plug them in to the original function. The original function was on the previous page. I do know that if you plug in 0, you get 2. On the other hand, I have no idea what you get when you plug in 2/3. So give me a second to do a little bit of smoke and mirrors here. If I plug in 2/3 here, I'm just going to figure this out on the board behind me and write down the answer. So pardon me as I do some scribbling on the board back here. If I plug in 2/3 there, I'll get 16 over 81. That's times 3. Minus, if I plug in 2/3 for the second x, I'm going to get 8 over 27. And then minus 2. First term, 3 is an 8, 127 times. Good, I got common denominators there. I mean, -54 over 27. Almost got it, folks. 16 minus 32 minus 54 over 27. 16 minus 32 is 16. So it's like -60 over 27. That reduces by 3 to -20 over 9. Okay, I think I know what it is. Part of the sidebar there. But I want to put some completion on this. If you plug 2/3 into the original equation, I know it wasn't a function, but I'm treating it like a function. If you plug in 2/3, and if I did my math correctly behind me, I think you get -20 over 9, which is even uglier than 2/3, but it is what it is. Alright, so it looks like I have 2 inflection points, one at 0 and one at 2/3, and one of the y coordinates is ugly. What does this look like? Well, let's put a graphing calculator and see. Well, it's from a college algebra lecture, so pardon the stuff that doesn't matter to you guys. No C. I believe it was a -2. Now, I'm probably going to have to play with the window quite a bit. Yeah, I am. Let me go back to a standard window. Hey, let's zoom in a little bit. This is starting to look right. One more. Okay, there we go. That looks pretty good. Alright, so here's what we said about the graph. In terms of the first derivative, we said that it was decreasing, and in terms of the second derivative, we said it was concave up. Notice the left end of this graph is going down and bowed upwards, so it is concave up. And when we hit 0, -2, the graph was still decreasing, but it switched concavity. So if you'll notice, it's bowed upwards and then it's bowed downwards briefly, but it's still decreasing. Somewhere in the middle here, and it's really hard to see. I'm going to zoom in and move down a little bit. So I want to show you this. Okay. Somewhere, well, it's at 2/3. I know where it is. It's at 2/3 right here. So if I go down to 2/3, right here there's an inflection point. They're kind of hard to eyeball, but notice that the left half of this chunk is concave down, and then suddenly it's concave up. That's where that inflection point is. But I'm still decreasing. And it decreased all the way until I got to this minimum, which we found at 1, -3. Then it's still increasing, and then it's still concave up. So this graph does everything that the derivative said it was going to. It was decreasing, flattened out, decreasing, and increased. It was concave up, concave down briefly, and then concave up again. So the derivative is saying everything that it's supposed to, and the graph is holding true to that. So is it a lot of work? Yes, but I told you on day 1, this is going to be one of the hardest math classes you ever had, because of the amount of stuff you had to do, and the amount of algebra behind it. Oh, how convenient. On the bottom of page 657 is the graph. Maybe I should have gone there first. Okay. What else in this section is there mechanically? Well, mechanically it's all the same. You take derivatives and you do stuff with them. I'm just going to pick one more example to do, and this is pretty much going to be it for 10.2, because I want to at least get through 10.3, and I'm afraid that's as far as I'm going to make it. Let's see. Well, I'm looking on page 660 at problems 13 through 18, which asks you to do pretty much everything we just did and sketch the graph. All of those are polynomial functions, which means they pretty much behave. So I'm not sure if there's a whole lot of discussion to have right there besides doing, excuse me, doing more of what you just saw. So, well, I really can't talk about 27 and 28 because they involve a graph that I can't get on the screen right now because I don't have a elbow in this room to make a projection. So let's just look at a word problem, and let's look at, oh, I'm tempted to look at number 35, but that one I'm going to leave for you because it's easy. Well, I'm going to talk about number 35 real quick. I'm going to jot down what's necessary, and I might end up doing the whole problem, who knows. This is on page 662, this is number 35. Alright. You're given a function, p of t, t probably stands for time, equals 27t plus 12t squared. Notice I make my t's with curvy bottoms so that you don't confuse it with the plus, minus t cubed. And let's see what this represents. Let's see, total number of units produced by worker in t hours on an 8-hour shift. Alright, so t is the number of workers. Really? Number of hours, excuse me. P of t is the number of, let's see, number of units produced. Alright, so there's the context of the problem. Here's the function. T is how many hours you work. T is the number of units that you produce. This is t hours of an 8-hour shift. 8-hour shift. So basically you can't work more than 8 hours. Okay, find the number of hours before production is maximized. Okay, so basically maximize P of t. Since I'm being asked for a maximum value, it's a first derivative issue, let me go ahead and write the second question and then we'll do both of them. B. Find the number of hours before the rate of production is maximized. Maximize the rate of production. Now be careful, the word rate means derivative, and the word maximize means solve the derivative equal to 0. So we're going to have to do 2 derivatives on part A. Excuse me, on part B. Alright, so for part A, all we have to do is find the derivative, set it equal to 0, find the critical values, and figure out who's the max and who's the min. So the derivative is 27 plus 24t minus 3t squared. We got to put that equal to 0. And then I'm going to do a little bit of shenanigans that I'll do in a situation like this. When you're solving an equation, it's always a good idea if your highest power is positive. And since my highest power is negative, I'm going to move everything over to the left side. That'll make the 3t squared positive, the 24t negative, and the 27 negative. It's not necessary, but I so prefer having a positive leading coefficient. And if you look closely, these are all divisible by 3, so I'm going to jump all over that too. Take out a 3, you get t squared minus 8t minus 9. And this will factor cleanly. This will factor into t minus 9 and t plus 1, I believe. Okay, so you get t equals 9, you get t equals negative 1. Now, I just said a second ago that this is during an 8-hour shift. So it makes me wonder, is the answer 9 or is it not? Because who's going to work negative 1 hours and 9 is longer than an 8-hour shift? Before we address that, let's just go ahead and continue this as a pure math problem, meaning who's high and who's low. Here's negative 1, here's 9. Let's see, I know the derivative is equal to 0, so these are the values of the derivative. Let's pick some numbers here, here, and here to figure out what the graph is increasing and decreasing. So if I put negative 2, let's try putting negative 2 in the derivative. Now be careful, the derivative is what was on the right before I moved it. Don't put it in here, that's the opposite sign of the derivative. If I put negative 2 up here, and again I'm going to kind of talk this out, this is negative 48 plus 27 is negative 21. And if I put negative 2 there, I'm going to get negative 12. So I think I get negative 33. Again, I'm not 100% sure it's 33, but I know it's negative. Trust me. I got to pick something between negative 1 and 9, about 0. That's always an easy number to use. If I put 0 in the derivative, we get 27, so it's positive. And if I put in 10, if I put 10 into the derivative, I'm going to get negative 300 plus 240. It's going to end up being negative. At this point, I don't care what the number is. I just know it's negative. So I'm going to make a note of that. What does that mean? Well, remember, first derivative tells you decreasing and increasing, decreasing, increasing, decreasing. So the question was, where do I have a maximum? Well, I might as well go ahead and summarize. There's a minimum at t equals negative 1, and there's a maximum at t equals 9. Now, my concern is the problem says on an 8-hour shift, and it says there's a maximum production at 9. So I'm going to flip to the back real quick. This is section 10.2. Look at the answer to number 35 and see if it addresses the fact that it said it was only an 8-hour shift. 10.35. It does. Because in the back it says t equals 8. So, my instincts were right. This is not being treated as a pure math problem. It's being treated in the context of the situation, which it should. So here's the to be continued, if you will. But here's the graph of P of t without any regard as to what the t can be. And I'm going to use the graphing calculator to graph it. So give me a second to go over here. It was, shoot, I don't even remember what it was, 27t. I got to use x in this calculator. Plus 12x squared. 12, please. Minus x cubed. And again, I'm going to have to change the settings on this window. Let's go to standard first. Alright. This graph is way high. You can insert your own joke there. I need to go much higher and much lower to see this graph. Let's go negative 15 to 50 and see if that does it. That's a little bit better. Now, the time can be all the way up to 8, so I need to go a lot higher to see how high this graph will go. Let's try 200. Better, but I still don't quite see where the graph reaches 8. So let's go to 1,000. Oops. And you can do this with any graphing calculator. I'm just trying to get a reasonable graph. Okay, now we're getting somewhere. Hey, look at 9. There's that maximum that I found. But here's the graph of your production function. And since you're talking about somebody who can only work an 8-hour shift, your time has to be between 0 and 8. So let me trim off the negative, most of the negative part of the x-axis. And let me trim off the extra fat up here. It looks like I can cap this at 500 and not lose the flavor of this graph. Alright, so here's the graph between negative 1 and a little bit beyond 8. Algebraically speaking, the high point on this graph is at 9. But we're only talking about between a 0 and 8-hour shift. So honestly, I can make my x-axis start at 0 and my x-axis stop at 8. So even though this graph peaks at 9, it gets chopped off at 8. Since the graph is increasing at that point, its high point is at the end of that interval. In other words, since I'm only going up to 9, since I'm only going up to 8, my graph stops while it's increasing. And if you stop the graph while it's going up, the point that you stop at is your maximum point. Even though it's not a critical value, it's an endpoint on that interval. Now, having said that, I get a funny feeling that this is probably mentioned back in 10.1 when I thought it was mentioned later in the chapter. I looked at 10.1, I don't remember seeing it. Maybe I didn't look at it closely enough. Yes I did. I'm looking on page 645, in case you have your book, and they have a picture of a graph that starts and stops at certain x values. Now in that graph, the maximum point is on the graph, and it's where it is. But whenever you chop off a graph, like we did on this one, your extrema can also occur at the ends. For example, and this will make sense, minimum production occurs when you work 0 hours. Duh! Maximum production occurs when you work 8 hours. It actually, if you were to work 9 hours based on this graph, you would peak your production rate, but it's probably OSHA or something that says you can't work more than 8 hours unless you get paid overtime. Let's go back to the question though, because the question was two-tiered. Maximize P of T and maximize the rate of production. I'm going to go back to the beginning of the question and make a stipulation on this T. We're actually defining a domain. Note, T is between 0 and 8. It doesn't say that, it implies it. It says the 8-hour shift, it implies the 0. So in terms of the graph, we only need to look between 0 and 8. And again, between 0 and 8, this graph is continually increasing. So if the graph starts out going up and it goes up for its entire time, then the low point is on the left and the high point is on the right, as was evident on this graph when we only went to 8. Okay, but there was a second question, which was to maximize the rate of production. Well, the rate of production, forgive me here, I'm going to erase this graph. And let me go ahead and write in words what needs to be written here. T is restricted between 0 and 8. Since P of T is increasing on 0, 8, and remember that's an interval, and I could have put brackets on it. The max is at T equals 8. And it didn't ask it. The min is at T equals 0. Just a little food for thought. If this graph were decreasing, then it would start high and end low. So the max would be on the left and the min would be on the right. Now as far as part B, maximize the rate of increase, or maximize the rate of change. Well, this is one of those buzzwords that we talked about in class. When you see rate in a calculus class, it means derivative. So in other words, maximize the rate of change means maximize the derivative. And maximize as a verb means solve the derivative of the derivative equals 0. So it's a second derivative equals 0 question. So we need to find the derivative of the derivative. Well, we already have the first derivative. The second derivative is 24 minus 16. Let me make sure about that. I'm doing it in my head. Yeah, that's right. All right. Well, that's easy to solve. I'm not going to do the math to get T equals 4. What is that? It's probably an inflection point. I can do a sign diagram, but since I have the graph up here, I might as well look at it. Look at 4. It's very difficult to tell, but on the left end of this graph, it is concave up barely, and on the right side, it's concave down. So at 4 hours, okay, let's back up for a second. I'm going to graph this function and its derivative. Its derivative was 27 plus 24x minus 3x squared. Remember, I have to use x's on this graphing calculator. So here's the derivative. It's always above 0, which means the derivative is always positive, which means the graph is always increasing. Here's the second derivative. The second derivative is 24 minus 6x. Now this is going to be a little bit harder to see. because it's way down here, but notice that your second derivative is 0 at 4. That means that's where your first derivative peaks, and it means it's where your function has an inflection point. So there's all kind of connections between the the function, first derivative, and the second derivative. But the fact that the second derivative is 0 at 4 means that your rate of change hits an extrema. In this case, the rate of change, the derivative, is at its highest at 4, which means that is when it's like the car's speeding up and then it slows down, but it's still accelerating, if that makes sense. At that point where it slows down, but it's still accelerating, it's where the first derivative would be positive, and that's where you would have an inflection point. This takes some time to digest, folks, so you might want to watch that and then watch it again, and then watch it again. All right, I'm going to go ahead and get to 10.3 because I really want to finish this section, and then I want to give you some problems to try. So here comes 10.3. 10.3 is called optimization. It's actually called optimization in business and economics, but optimization basically means maximizing and minimizing. It can be either one, a high point or a low point, depending upon the context of the situation. Back up for a second, I think I left something out, 10.2. Did I leave out the second derivative test? I believe I did. Yes, I did. There's something in the second section called the second derivative test. It basically predicts high and low points without the need for a sign diagram. So, pardon me for a second, let me back up for a moment. 10.2. It's called the second derivative test. And it's used to determine who's a high point and who's a low point without needing sign diagrams. And it goes something like this. Suppose x equals c is a critical value. And remember, that means it makes the derivative 0 or undefined. For now, let's just assume it's 0. If the second derivative at c is positive, then there is a minimum at x equals c. And then the opposite of that statement as well. If the second derivative is negative at that number, then there is a maximum at x equals c. I used to always get these confused when I first took calculus, because you would think positive would mean maximum and negative would be minimum. But the easiest way to remember is to remember what positive and negative second derivative means. A positive second derivative means concave up, and a negative second derivative means concave down. Well, this one has the minimum, and this one has the maximum. So if you can visualize concave up having a low point, concave down having a high point, I'm going to erase those arrows going out of the parabola, they just don't look right there. So if you can visualize that, then it's easy to remember which sign tells you what. So there is a way to calculate whether or not an extrema is a max or a min without having to do a sign diagram. Warning though, if the second derivative is equal to 0, and that should be a c. If the second derivative of c equals 0, that tells you nothing. It tells you nothing about being a high point or a low point. If you want an example, look at f of x equals x to the 4th. Its second derivative, it has a critical value of 0. If the second derivative is 0, then it doesn't tell you if it's a high or a low point. It's a low point though. Alright, so it can be a high point, a low point, or it can just be nothing. So it doesn't tell you anything. Alright, let's get back to optimization. We've kind of already done this. Optimization is basically maximizing and minimizing a function on a given interval. So let me show you a non-business example, and then I'll show you a business example, and that's pretty much all I'm going to be able to do from this section. Alright, I'm going to go straight to the textbook homework problems and pull something out of there. For example, let's look at maximizing revenue. We're going to look at question 8 on page 671. Page 671, number 8. Let's see what we're getting. Firm has total revenues given by this. R of x equals 2800x minus 8x squared minus x cubed. Okay, so there's our revenue function. Find the maximum revenue. Now notice it's not asking for the x, it's asking for the maximum revenue. So we'll find an x and put it in the revenue function. So the first thing we're going to do is take the first derivative, which is 2800 minus 16x minus 3x squared. Seriously? Okay, it is what it is. We got to solve that equal to 0. I said seriously because I was expecting a greatest common factor to factor out, unless I took the derivative wrong or wrote something down wrong. No, it is what it is. Alright, we're going to have to solve this. I'm going to move everything to the left because of this equation. You can do that with an equation, you can't do it with the function. Once it becomes an equation, you move stuff around. I like to leave the coefficient positive. You might be tempted to get out the quadratic formula. I'm going to hope this factors and see if I can factor it somewhat instantly. Although getting that 16 in the middle is going to be tricky. Well, let's see. I know I have to have 3x and 3x, and pardon me, I'm going to pull out some crazy algebra moves here in a second. I need to get 16. I can't put zeros on both because it has a 0 in the middle, so I'd have to have 0 in the end. But 300 here, 28, 100 here. No, I think it's going to be 100 here and 28 there. I'm not 100% sure. 28 times 3 is 84. Yeah, it's going to work. All right. Now, you could use the quadratic formula. But for the sake of moving this problem forward, let's pretend it gets factored into this, which gives you two x values, 28, and this one will give you negative 100 over 3. One of these I can throw away instantly. X is the number of units produced. I can't let x be this for two reasons. Number one, it's negative, and number two, it's a fraction. You can't produce a fraction of a unit and sell it, and you can't produce a negative number of units. So in the context of this problem, I can throw that out right away. It seems like my critical value is 28. However, there's no guarantee that it is a max or a minimum. So I'm going to use the second derivative test to verify whether or not it's a max or a minimum. So this is continued. Okay, new page. So let's use the second derivative test. Good thing I backed up and picked that up. Use second derivative test. Which means I need to know the second derivative of my revenue function. Well, the second derivative of my revenue function is negative 16. Am I looking at the right thing? Hold up, folks. Derivative, yeah, negative 16 minus 6x. Minus 6x. Alright, let's plug in our critical value, which was 28. Into negative 16 minus 6x. I don't need to even do this. I know it's going to be negative. Look at it. It's a negative plus a bigger negative. It's a bigger negative. So what that tells you is concave down. And if the graph is concave down, that means that it has a maximum. So the second derivative tells you that there's a maximum that x equals 28. That is not the answer to the question. The question was, what's the maximum revenue? And so the maximum revenue is whatever you get when you plug 28 into the original function. I will leave it up to you to plug in and do the math because that's just arithmetic. Alright, so that one was pretty straightforward. There is one more that I would like to do, at least, and it's actually number 9. I like number 9 because I'll probably give you one like number 10 on your test, because I'll probably do one like it on your final. So this is the same page in number 9. It's got a few more words, but I'm going to try to trim the fat. An agency charges $100 per person for a trip to a concert if 70 people travel in a group. So 70 people means that it's $100 per person. That would be $7,000 of revenue if you think about it. But there's a catch to it. For each person above 70, the charge is reduced by $1. So for each person above 70, like a discount, you lower the price by $1. And the question is, how many people maximize their revenue if the trip is limited to at most 90 people? So if the trip is limited to 90 people, how many people maximize the revenue? All right. We're going to do this question as if there's not a limit, and then go back and address the limit issue. So let's start by trying to figure out how to set up a revenue function. Well, first we need to figure out what x equals. You might think x should be the number of people, but it's actually better in a situation like this to describe what x is relative to your given information. For example, 70 people, $100 a person. For each person above 70, and that's what I'm going to let x equal. I'm going to let x equal the number of people above 70. So for example, if 75 people came, then my x would be 5. If 80 people came, then my x would be 10. How do you find the revenue? Well, in order to find revenue, R of x, it's the price per person times the number of people. Remember, I need it in terms of x. Well, let's think about the number of people for a second. If x is the number of people above 70, then this is how many people I have. 70 plus the extra above 70. What's the price they were charged? Well, originally the price is $100, but then you subtract $1 for every person above 70. I wrote the 1 there because if it were a different price, I would have to put the number there. So in terms of the number of people above 70, this is what my revenue function would be. Since I'm going to be taking the derivative of this, I think it would be probably a good idea to FOIL this out. If you were to FOIL this out and arrange it, you would get negative x squared plus 30x plus 7,000. Alright, so I have my revenue function, and I already know what I'm looking for. This is a parabola, it's upside down. I need to find its high point and see if that's where I'm going to maximize my revenue. So, we'll continue this one. Do a new page. We need to maximize R of x. I'm going to be a little more specific here. On the following interval, the fewest number of people we can have is 0, and we have a cap of 90. I'm going to flip to 10.4 because I'm trying to see something here.